So one of the things that's really important about serial data communications is that it goes over wires, and all signals on wires are susceptible to interference from other devices around them. If you ever look at the back of your charger, for instance, you'll see that there's a number of symbols on it. Those symbols say that it relates, that it meets certain specifications, and some of those are to do with electromagnetic interference, or EMI, or RFI, radio frequency interference, or something like that. You'll see that on the back of the charger, some of those symbols. And what that means then is that if we've got a data which is going through like D0 to D7, we might end up missing a bit. So for instance, a 1 could be changed to a 0, or a 0 could be changed to a 1 because of some outside interference. And what we do is we have a little system where we can detect errors, certain errors within limits, to say, hey, the data was corrupted on the way. What was sent isn't what was received. And what we do to do that is we add an extra bit to our data, and it's called a parity bit. So the way this works is that we add up all the number of ones in this, including the parity bit, and if it's an even-based system, then it should be an even number of ones. So 1, 0, 1, 0, 1, 0, 1, 0, 1. What's in here is 1, 2, 3, 4, 5 ones. Now we're not going to include the stop bit in this. So we've got 5 bits of data, including the parity bit, and we have an odd number of these. Now, if the system is set up to be even parity, then that's an error is indicated. Somewhere along the line, one of those bits has changed from a 0 to a 1, or a 1 to a 0. In the second one, we have 1, 2, 3, 4, 5, 6, 7 ones. So again, including the parity bit, but not including the stop bit. So, and if this is an odd system, then yes, that data is likely to be correct. And the next one, again, we have an odd-based system, so we're looking for an odd number of ones. 1, 2, 3, 4, 5, 6, 7. So we have an odd number of ones, so yes, the data is correct. Well, actually, is the data likely to be correct is the question, because it certainly could occur where 2 bits changed. So that could have been 0, 1 and it changed to 1, 0. We wouldn't detect it. So there are some limitations in this system. But this is a very simple system of checking whether data has been corrupted or not. And it's not a system for fixing the data. We've no idea what the error was, just that the right number of bits did not turn up. Okay, so that's it. Now let's just go down and have a look at the data sheet. We've got a great deal of options in the data sheet. We've got a very high resolution baud rate generator. That's the sort of thing that manufacturers like to write, that they can make really good stuff. That's what they're saying here. We can check out the errors a little bit later. Now, for instance, this will send asynchronous or synchronous. So again, asynchronous means that means that there's no clock signal sent. Synchronous means that there's a second wire at least with a clock signal on it. We can have full duplex, independent receive and transmit registers in it. We can set up with 5, 6, 7, 8 or 9 data bits and 1 or 2 stop bits. We can't change the number of start bits, it's fixed at 1. We can have odd or even parity generation and parity checks supported by hardware. So you can imagine there's a simple little FSM in there probably, finite state machine, just checking to see whether the number of bits, and it will output it if they're correct, okay? We won't go into many of the others. Oh, there's a number of interrupts that we can use, and we'll look at those now. Let's have a look at a bit of an example. So I've set this up here to run at 8 megahertz using 8 data bits, 1 start bit, 1 stop bit, and at 9600 baud. So the first thing to do is that you need to put in your oscillator for your crystal frequency that you're using. Now, I know in the boards we're using at 16 megahertz, and in the Practorials I've set it up and explained that it's 16 megahertz. we're using a baud rate of 9600, and here is the parameter that we need to calculate, and this is how we do the calculation to do this. Now, the other thing I want to point out here is we do not use magic numbers. You'll see a number of examples on the internet about using serial data communications for the AVR, and they will just pop magic numbers straight in, and you'll have to figure out which bit it is and what it's setting. Much better to set this. So let's just have a look at the data sheet. We're looking for register 0B. Now notice I've just popped a 0 in here. You won't have seen that in your notes, but on our AVRs we actually got USART 0, so we'll need to put that in there. That's already shown in the factorials as well. So let's just open up our data sheet. We're looking for, remember there's a little glitch in the in this data sheet here in terms of the formatting. So just come down here, we're looking at our registers. So let's look at our register A. No, it was register B that we were setting. So we've got these two bits here. There we go, bits 3 and bit 4 are how we enable transmit and how we enable receive. We must do them independently. If we're only using one, then there's only one need to do that. And of course, they're on pins D0 and D1 of the microcontroller. And they're flagged as to exactly which one is transmit and which one is receive. You can't change those functions using the USART, they are fixed. Okay, let's go back to, there we go. Now let's have a look at this register C. Again, I've inserted the 0 there because it wasn't in these notes. And we're setting these two bits, UCS700Z00 and UCS-Z01. We're going to look up to see that this is all the options that we're getting here by setting these bits. So back to the data sheet. Again, total familiarity with this data sheet, finding your way around it. And what we're doing is we're setting up these two bits here, UCS-Z00 and UCS-Z01. And if we scroll down here, we will see a little table that will help us set them up. Here it is. Oh, we've actually got 3 bits. Let's just have a look to make sure we identify where all 3 bits are. Okay, so there's 0, there's 1. You'll have to go searching to find out where is the the 3rd bit. So that's UCSZ02 is the one you're looking for. It'll be in one of the other registers. So they like to do this. They split these bits up between different registers because they make different devices at different times and they expand the features, and then they realize they need another bit. So they just stick it in a different register. You have to get used to that. So here we go. This is how we set up whether it's 5, 6, 7 or 9 bit. Okay. And here's our bit settings here. The number of stop bits. And by default, it is 1. So we're not setting this bit, which means that it's 1 bit stop bit. Okay, there's 1 stop bit. Anything else here? No, the parity mode at the moment, we're not using any parity. Oh, in fact, no, I think, did I say parity in that example? No parity, there we go. So we're not using that bit. So some of these are by default and some of them need setting, of course. And of course, then we need to write into UBRR this parameter which defines our baud rate. And you'll find UBRR is one of those registers down here. There we go, it's actually 16 bits and you have to write into it the right value. This is a 12-bit register that contains the baud rate. So baud and bits per second being equivalent in this context, okay? And that's it. So that's setting it up. Now what I want to do is just say this is for transmitting, and I explain this in the factorial, and you need to go and have a look at this in operation. But here we are, basically we throw a byte at the register and then we wait for it to clock out. So we throw a byte into here and it's automatically going to shift it out, and it's going to add any parity that we want, and it's going to add the start and stop bits. It's all automatic for us. We don't have to write that. You could, of course, write your own transmit function using a timer and write it in software and stick a transmit on any pin you wanted to. That's really quite feasible. I've done that before myself. Receive. So here's how we set up our our baud rate generator, okay, in this 16-bit register up here. We have a separate receive register and a separate receive line, which means, of course, we can operate this as full duplex if we want to. Here I've set it up for both transmit and receive, but I'm not actually using the receive. Basically, we throw a byte at the register and it just clocks it out for us. Now, the thing about this is it's not an interrupt-based system. It's a blocking system. So this code here is blocking. Now that's not too bad in terms of blocking, because what we're doing is we're just waiting until it's sent out all those bits and then coming back to our program. So at 9600 baud, each one of those characters takes, or each one of those bits takes 104 milliseconds. So we've got 8 data bits, start and stop bits, so that's 10. So 10 times 100 microseconds, 1 millisecond to send this data out. So our whole microcontroller is locked up for a millisecond, it's blocked for a millisecond while this is happening. So if that's a problem for you, then you need to investigate how to use an interrupt to send the data, okay? And what I'm going to do is I'm going to show you what happens on the receive side. And this is not covered in the Practorials. We're not doing any practical demonstration at the stage of receiving serial data into the microcontroller. But what's happening here is we've got some data that we want to send, that we've got some data that we want to receive. And what we do is we wait for the data to come in. And of course, this is blocking. And if nothing ever arrives, then the code will never go on. Okay, so you can write all sorts of funny things you like around this in terms of maybe set up a timer and check this every now and again to see if any data has arrived. But there's a slightly better way, and that is to use the interrupt. And so what I've got down here is the ability to use interrupts. I've just pointed at this code. Basically, when data arrives, write it into our variable. And then we go back to our main processing. And every time data arrives, we can write it into our variable. So this is a really interesting way of just looking at this. I'm not going to go into this in any detail. The fact that you're beginning to understand that we use interrupts so that our devices are responsive and reactive to the real world. We avoid blocking where we can to stop our devices from blocking things in the real world from happening or being detected. And really it's just a matter of getting that concept in your mind and knowing that, hey, I can't afford this to block. I need my device to be more responsive and reactive to this. How do I do this? And then go looking for the interrupts, okay, to figure out how to use them. And look, just for your own interest, I've just popped in this as a reference. I think there's some good stuff here. In the future, if you're playing with this, don't have a look at it now. If you don't want to, that's fine. So that's where we're going to stop for this lecture, and then I'm going to jump back into my sequence again.